The purpose of our project was to identify the physics of motion using predetermined lengths of a pendulum while keeping the mass of the object attached the same. A pendulum can be defined as a weight hung from a fixed point so that it can freely swing back and forth. The physics of a pendulum system can be described as being displaced sideways from its resting position. A restoring force due to gravity will then make it accelerate back towards the equilibrium position. Frequency can be defined as the number of cycles per second in an oscillation. Both frequency and period are inverses of each other. For the setup, a yardstick was placed in the frame for reference, while the string was attached at a fixed point to the counter. On the end, an empty soda can was attached. The first trial used a length of 0.2 meters. After being analyzed in the Vernier Video Analysis app, a line of best fit was placed and all the data points were put into Excel for calculations. We then repeated the same steps for our next trial at 0.4 meters and again ran it through the Vernier Video Analysis app to obtain the data needed. Finally, for the last trial, we set up the experiment in the same way but used the predetermined length of 0.6 meters. After the analysis was done, we could then begin our calculations. To find the period in each trial, we used the equation of 2 pi times the square root of length over gravity, which gave us the values of 0.897 seconds, 1.269 seconds, and 1.554 seconds. Each consecutive trial had an increase in speed of about 0.3 seconds. We also calculated the frequency, but since it is just the inverse of the period, we used the equation of F equals 1 over 2 pi times the square root of G over L. This then yielded values in hertz rather than seconds. After data collection, we were able to see that each trial had an increase of about 0.3 seconds as the length increased. For the frequency, we did not see a consistent drop like the period increments, but this could be due to human error.
We then compared our experimental periods to the calculated periods and calculated a percent discrepancy between the two values. In order to find our experimental period, we used the values for b from the cosine fit of our graphs and applied them to the equation b over 2 over pi. When observing the percent discrepancies, we found that the discrepancy for the 0.2 meter string was the highest. Overall, all of the experimental periods were longer than the expected values, which could have been the result of many factors such as the video analysis app used or air resistance. More trials for each string length may have brought the expected values closer to the observed ones.